Let me ask you a simple question. Can education really increase how much you earn? The answer is probably yes. But how can you prove it? Well, the evidence begins with a regression table like this. Economists regularly publish this, and almost every argument about wages, prices, and policy ends up resting on this one tiny symbol, the asterisk. It looks like decoration, but it's not. It is the proof. Behind that star is an entire mechanism. One line fighting through a cloud of noise, thousands of parallel samples we never see, a bell curve that shows up everywhere, and a single ratio that decides the fate of the result. For the rest of the video, we'll run the hidden mechanism piece by piece, and we'll see how this star forms. Here is an equation you have almost certainly seen before. The equation of simple linear regression. And with it, economists make claims about almost anything we can measure. Y is the variable we are trying to explain. X is the variable that influences Y. Alpha is just where the line starts. Beta is the slope. It tells us how much Y moves when X moves by a single unit. And epsilon is everything else. Every other influence on Y that this simple line leaves out. But in the real world, we never see the true beta. So we estimate. And the estimate is a different equation. Heads on everything. And notice what's missing. The epsilon. A fitted line makes no error claim. Whatever it misses becomes the residuals. The estimated beta and the star attached to it quietly becomes the entire argument. With stars, the result feels real. Without them, it feels weak. But as we know by now, the star is not where the story begins, it's where the story ends. Let's leave the symbol for a moment and look at the data. Here's our observation. Each dot is one unit, I mean one person, one household, or the subject of our study with two continuous variables, x and y. But they do not fall on a perfect line. They form a space. Let's call this space a cloud of observations. The equation promised us a line, but there are infinitely many lines we can draw through this cloud. Each is a different guess about beta. So the first real question is, out of all these possible lines, which one is the best? And what does best even mean? To answer that, we need to find out how wrong a line is. Pick any line and look at a single point. The gap between the point and the line is the error that line makes on that one observation. We call it the residual. Do that for every point, and we get a whole set of residuals. Now we have something to work with. Because if we can turn all those little misses into a single number, we can finally compare different lines head to head. The best line will be the one with the lowest score. So how do we combine all those residuals into one number? The obvious idea is just add them up. But that fails immediately. Look, some points are above the line, some below. This means positive misses and negative misses. Add them together and they cancel out. A terrible line, wildly wrong in both directions, could score a perfect 0. It makes raw sum useless. So we have to get rid of the signs. One way is to take the absolute value of each residual. Just treat every miss as a positive distance. That actually works, and it even has a name. Least absolute deviations. But it's more forgiving of wild outliers. There's a different move that turns out to be far more powerful. Instead of the absolute value, we square each residual. Squaring does two things. First, it kills the sign. Second, and more importantly, it punishes big mistakes far more than small ones. A miss of 5 becomes 25, but a miss of 10 becomes 100, 4 times as costly. So squaring sends a clear instruction. Small errors are fine, but do not under any circumstance miss badly. Add up all those squared areas and get a single number, the sum of squared errors, one score for the whole line. So the best line is just the line that makes the score as small as possible. Actually, there's another important reason we choose squares over absolute values. Let's emphasize this statement. Make the score as small as possible. That sentence is doing a lot of work. It has quietly turned our line fitting problem into something else entirely, an optimization problem. Think of it this way. Every possible line is defined by two numbers, its intercept and its slope. So instead of picturing lines in the data, let's picture a landscape where the ground beneath the feet is these two numbers and the height is the score that line earns. Because we squared the errors, the surface becomes a smooth bowl, and in ordinary cases, a single gentle valley with exactly one lowest point. So finding the best line is just rolling downhill until we can't go any lower. When a computer runs a regression, this is what it's actually doing. Not drawing a line by eye, solving an optimization problem, and landing at the bottom of the bowl. The formula for the slope tells a story about the data. The top measures how x and y move together, and the bottom measures how much x move on its own. That's the whole intuition. The slope is the co-movement divided by the x's own variation. If x and y move together strongly relative to how much x varies, the line tilts more. And one more quick fact. With an intercept in the model, the baseline always passes through a single point, the average of x and the average of y, dead center of the cloud. So the line is anchored at the heart of the data, tilted by the covariance. We found it by minimizing squared vertical distances. But there is a second way to arrive at this exact same line, a way that has nothing to do with vertical gaps and everything to do with geometry. And honestly, it's the most beautiful idea in all of regression. To see it, we have to change how we look at the data completely. Until now, each dot was a point on a graph. Forget that. Instead, imagine taking the entire column of y values and treating it as a single arrow reaching out into space. All the predictions our model is capable of making don't fill the whole space. They live inside a flat surface passing through the origin. We call it a prediction space. Every point on that surface is one possible fitted vector y hat. But our data arrow points off in its own direction because real data is noisy. So the question becomes, of all the predictions we could make, which one is closest to the truth? Watch what happens when we drop the arrow straight down onto the surface. The closest point is the shadow, the spot directly beneath the tip of the arrow. And that little connector between the arrow and its shadow is the residual. And here is the magic. The leftover arrow meets the surface at a perfect right angle. That's exactly perpendicular. That perpendicularity is not a coincidence, it's the entire point. It says that after we have fit the model, whatever is left over has no straight line relationship with x remaining on it. We have squeezed out every last drop of linear information x had to offer. What's left is pure leftover. So least squares isn't really drawing a line through dots. It's casting a shadow. It's finding the one prediction inside the space of everything we could predict that sits directly beneath the truth. Vertical distances in a scatter plot and a perpendicular shadow in high dimensional space, they are the same answer seen two different ways. Okay, we now have our line. It's look final. One intercept, one slope sitting confidently at the bottom of the bowl. But that confidence is an illusion because everything we just did depends on the data we happen to collect. And data is random. Here's a thought experiment. Suppose we could run our study again. Same population, same question, but a fresh sample of observations. We would get slightly different dots and a slightly different baseline. Every sample gives us a new cloud and every cloud gives us a new slope. So this number we have been treating as fixed, beta hat, was never really one number at all. It depends entirely on which particular sample landed in our hands. Change the sample, change the estimate. This randomness in our estimate is nothing more than the randomness in the error. So beta hat is not a fixed fact about the world. It is random, a quantity that comes out differently every time the dice are rolled. And if the slope is different in every sample, then there is not one slope. There is a whole distribution of slopes we might have gotten. Imagine 1,000 samples, 1,000 best fit lines, all drawn on top of one another. They cluster. Most of them tilts at roughly the same angle, a few leaning more or less deeply. Now take just the slopes, 1,000 values of beta head, and stack them up into a histogram. That shape is the sampling distribution of beta head. It's the answer to the specific question, what range of estimates could this study have produced? Two features to consider here. First, where it's centered, for a well-behaved model, right around the true beta. And second, the one we have been chasing since whole time, how wide it is. That width has a name we have seen many times, the standard error. And what makes it wide or narrow? Again, two things. The first is noise. If the dot scattered far from the line, the estimate wobbles more and the standard error grows. The second is the spread of x. Think of x as a lever. If our x values are all bounced together, we are trying to balance a line on a tiny fulcrum. If our x values are spread far apart, we have a long, stable lever and the slope is pinned down firmly. So a precise estimate needs a wall that isn't too noisy and x that varies enough to reveal the relationship in the first place. Which raises the obvious question, the one every researcher asks. Can't we just collect more data? And if we do, how much does it actually help? There's a law that answers the first half, the law of large numbers. Flip a fair coin 10 times, we might get 7 heads. Flip it 10,000 times, and we will land very close to half. As we average more and more independent observations, the average settles towards the truth. The same thing happens inside the regression formula. As the sample grows, that noise average pulls towards the zero, and beta head gets dragged towards true beta. In simple terms, more data means closer to the truth. But notice carefully what this law does and does not tell us. It tells us the estimate settles down, and it even tells us where on the truth. What it doesn't describe is the shape of uncertainty that remains along the way. For that, we need one of the most surprising and beautiful facts in math. Take a bunch of random observations. It doesn't matter what their own distribution is, skewed, lopsided, spiky, flat. Add many of them together or average them. They become a bell, the same smooth symmetric curve over and over. This is the central limit theorem. It's the reason the bell curve shows up everywhere, because so much of the world is a sum of many small independent influences. And our estimate is exactly that kind of thing. Beta head carries an average of all those little error terms. So the central limit theorem guarantees that as the sample grows, its sampling distribution is that same bell. And the theorem tells us something even more practical. Exactly how fast the bell narrows as we add data. The width shrinks in proportion to 1 over the square root of the sample size. If we gather a truly enormous dataset, the standard error can shrink to almost nothing, which means even a microscopic relationship, an effect so small it's practically meaningless, can be pinned down with extraordinary precision. Hold on to that thought, because we finally have both halves of the puzzle, an estimate and a full bell-shaped measure of how much it wobbles. We are at last ready to test it. Here's the question a regression is really trying to answer. Is there a relationship at all? Is beta genuinely different from zero, or could this tilt in our line just be noise? To decide, we cannot look at the slope by itself. A slope of 2 might be enormous, or it might be nothing. It depends entirely on how much that slope wobbles. So we build a ratio. We take the estimate and divide it by its standard error. This is the t-statistics, and it answers one very specific question. How many standard errors away from zero is our estimate? Put simply, T-statistics is signal divided by noise. And this is exactly why the size of a coefficient can be deceptive. Picture two studies that both estimate a slope of 2. In the first, the standard error is 1 that make a t of 2. In the second, the standard error is only 2/10 and thus a t of 10. Identical slopes, wildly different signals, because one was estimated in a noisy world and another in a precise one. So the thing that will eventually earn a star was never the size of the effect. It's the size of the effect relative to its wobble. Now we have our signal to noise number. But a number alone can't tell us whether it's big enough to take seriously. Statistics has a particular way of testing a claim. Instead of trying to prove that a relationship exists, it starts by assuming the opposite, and then checks whether the data can live with that assumption. So we imagine a world in which the beta is exactly 0, no relationship between x and y. This is the null hypothesis. In that null world, our t-statistics wouldn't come out to 0 every time, because random sampling would still push it around a little, but it would almost always land near 0, and its value would trace out a familiar bell. Technically, it's a slightly heavier tailed cousin of normal curve, called the t-distribution, which is where the t-statistics gets its name. With enough data, the two are practically identical. Now we drop our actual, observed t-statistics onto the picture. If it lands near the middle, our data looks perfectly ordinary for a world with no relationship. But if it's land way out in the tail, far from where the null world expects it, then something is off. Either we got very unlucky or the null world is simply wrong. The p-value measures exactly that. It is the probability in the null world of seeing a t-statistics at least as extreme as the one we actually got. A small p-value means if there really were no relationship, data like ours would be a genuine surprise. So we start to doubt the null. But we have to be careful about what the number is. The p-value is the probability of the data assuming the null is true. It is not the probability that the null is true given the data. So a small p-value does not mean the effect is large. It means our data would be surprising in a world where nothing was going on. There's one more way to tell this exact same story. Instead of asking whether 0 is surprising, we can just draw a range of slopes that are believable given our data. We start at our estimate and reach out in both directions by a critical value times the standard error. That gives us a band. This is the confidence interval. Think of it as the set of slopes that are still plausible after seeing the data, a fuzzy zone around our best guess. Now watch what happens to 0. If 0 falls outside the band, then the estimate is what we would call statistically significant. But if 0 falls inside the band, then we cannot rule out that there's no relationship. So asking is 0 outside the interval and asking is p-value small are identical questions as long as the levels match. 0 outside the 95% interval is exactly the same statement as a p-value below 5%. Same uncertainty, two languages. Now finally, we have every single piece we need. Let's build a star. The star is nothing more than a threshold. If the p-value drops below 10%, 1 star, below 5%, 2, below 1%, 3. But it's not written in stone. We can change it and even use other signs instead of star. But look at everything that had to happen for that light to switch on. Let's run it all from the beginning. Optimization, geometry, randomness, probability, and a threshold, all of it compressed into a single symbol. So the star is real, it means something. But now that we have seen the mechanism, we can also see clearly what the star does not and cannot tell us. First, a star is not a measure of importance. Remember the central limit theorem and how the standard error shrinks with more data? In a giant dataset, an effect so small it barely exists can still cross the threshold and collect the stars, simply because it was measured with enormous precision. A star tells us an effect is precisely estimated. It says nothing about whether the effect is big enough to matter in the real world. Precision is not importance. Second, and this is the most important of all, a star is not proof of causation. Suppose we regress wages on the years of education and get a beautiful 3-star coefficient. It's tempting to conclude that education causes higher wages, but that coefficient could be picked up by ability or family background or the quality of school or the strength of the local job market. Anything that happens to move alongside education and also affects wages. The star has no idea. It measures how precise the association is. It cannot tell us whether X is causing Y or whether something else is quietly driving both. Regression coefficient doesn't solve omitted variables. It doesn't solve reverse causality. It doesn't solve selection. Causation is a question of research design of experiments and careful identification. It is a completely different problem from the one the star solves. And third, the star is fragile. It leans on assumptions we made along the way about the errors, their independence, their constant spread. Break one of them and the standard error change. And once the standard error moves, watch the whole chain react. The t-statistic shifts, the p-value shifts, and the star can appear or quietly vanish. So the star is not a verdict. It is a signal produced by a model, valid only as far as the model's assumptions hold. Let's go back now to where we started. A regression table, a row of numbers, a little star at the end. Only now we don't see the star. We see everything behind it. The next time a coefficient has stars in our paper, we will know the right question to ask. Not just is it significant, but how large it is really. Is the interval narrow because the effect is strong or because the sample is huge? Are the assumptions behind the standard error actually true? And is it a causation or just a correlation dressed up in star?